Okay, let's get started. Any questions about the assignments? Undergraduates, you're working on assignment 5. Grad students, you are approaching the end, 9 and 10. All good? Okay, let's jump right back into lecture. We're looking at some of the early experiments in evolutionary robotics, and we made it partway through lecture 9 last time on minimal cognition. We're looking at 4 different experiments. In each of the 4 experiments, we've tried to pare down the complexity of the robot and its task environment. The neural network controlling the robot is not that minimal, it's a CTRNN. While these minimal robots are evolving, evolution is tinkering with the taus and the weights and the thetas and the gains of the neural networks, which may or may not be useful depending on the particular kind of cognition building block we're looking at. We're on the second of 4 of those experiments. We'll finish those off today. And we'll start in on lecture 10 today, which is definitely not a minimal robot, but it continues in this tradition of trying to evolve robots to exhibit initially simple building blocks and gradually scaling up to slightly more complex building blocks of intelligence. And ACP, as we'll see in lecture 10, is not necessarily a trivial thing to do. Okay, that'll conclude our discussion of the first few experiments, and then we'll switch and talk about movement next week. We'll focus on movement next week. Okay. So we ended last time by looking at the robot that evolved to perceive affordances, and today we're going to be looking at memory, obviously a building block of intelligence. How do we evolve a robot that's capable of remembering things? We can include recurrent synapses in the CTRNN, which allows the robot to remember things if it's necessary, but what kinds of tasks require memory? Here's the simplest possible thing you can imagine. We have, sorry, we're not on memory yet. I gave away the punchline. That's going to be number 3. We're looking at self, non-self discrimination first. Okay, we have our immobile robot sitting at the bottom center of the screen. It has a single arm and a single hand, and it can wave that arm left and right in front of it. It has 2 motor neurons pulling to the left or pulling to the right. And we've got, as usual, these 7 ray sensors that are reporting at every time step the length of those rays. The rays can either collide with the falling object or the hand. Imagine this particular falling object here comes and breaks the dotted hemisphere here in front of the robot right here. The robot is then seeing the object, but it's probably also seeing its hand, and how can the robot distinguish between object and hand? In both cases, a ray sensor would be reporting a pretty short length. How would the robot distinguish between self and non-self? Any ideas? Scott?
Move its hand and see if it sees the signal change.
Exactly. We talked about a robot already that learned to distinguish between self and non-self, and the way that it did that is by saying, when I send commands to my motors, I see something in my environment start moving, and when I stop sending commands to my motors, suddenly I see that thing stop moving. That's the definition of self, a combination of motion and perception. What was the robot we saw already that was able to do that? BabyBot from MIT, right? That humanoid robot that was pushing the fruit in front of it, right? So here's an even simpler example of that. Okay, so I think we ended by looking at the fitness function last time, which was to try and minimize theta sub I. Again, for each controller, we're going to drop multiple objects and sum the average ability of the robot to catch the object. The object is going to hit this dotted hemisphere in front of the robot, and whatever angle in front of the robot that object hits at, its arm should also have exactly the same angle. Its hand should be co-located with the object when the object gets there. If it does, it has a theta sub I of 0, larger angle, it did a worse job. Make sense? Okay, so we're not going to talk about the evolutionary algorithm, evolve, 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 evolve. take the best evolved controller and put it back into the robot and evaluate that controller thousands of times more and look at that controller's mean performance in situations it has not seen before, which gives us this plot down here. They dropped a huge number of objects that hit either minus pi over 8 radians to the front left of the robot, or all the way up to positive pi over 8 radians in front of the robot. So the object was hitting left, center, right of the robot. And then they looked at the angle of the arm when that object hit. How did the robot do? So each dot here corresponds to one of these object placements where it hit in front of the robot, and the height of that dot represents the angle of the arm when that object hit at that location. And these bands here, these vertical bands, represent error bars, how sure we are of the mean, which is the dot. So the dot, as far as we know, probably lies somewhere in this vertical band.
Looks like it did very well.
It did very well. So if we look right at the center of the plot, 0, 0, that means that the object hit front center of the robot, and generally speaking, the arm was more or less at 0. Maybe a little bit negative, maybe a little bit positive, but not too bad. It did generally pretty well. When the object hit to the robot's right, its arm was right. And when the object hit to the robot's left, its hand was left. It did more or less the right thing. It had a few places where it had kind of a harder time. What are they?
In the center, where the object angle is 0.
In the center, there seems to be these bars are a little bit taller. It's having a little bit of a harder time here. We probably know from the previous experiment that maybe there were some conditions here that were occurring in the center that the robot never saw during evolution. But generally speaking, it did pretty well. Okay. Let's have a look at how the robot did this. Every year I explain this plot, and I probably make one mistake, so pay attention here and catch me if I make a mistake. Takes a little bit to explain this one. All right, so let's start at the bottom center of this plot. At the bottom center of this plot, this represents the object falling and hitting directly in front of the robot, not to the left and not to the right. And each of these trajectories is describing the motion of the robot's arm as the object is falling and then hits in front of the robot. We're playing back just one evolved controller now. And they did two sets of replays. In the first set, the trajectories that you see to the left, they took the robot's arm and ratcheted the arm all the way to minus pi over 8 radians. So the robot started with its arm rotated pi over 8 radians to the left, and then they dropped the object, and the object fell and hit in front of the robot. In the second set of trials with the same controller, they rotated the robot's arm to plus pi over 8 radians, dropped the object, and the objects fell and hit to the center. So far, so good. So you can see these two groups of trajectories, which is the robot starting with its arm to the left or to the right. The shading, the grayscale of each individual trajectory represents where above the robot they dropped the object. They could drop the object anywhere above the robot, but the object would fall diagonally and always hit front center of the robot. So if we look at this color bar at the top, dark trajectories represent that the object was dropped top left, and light trajectories represent that the objects were dropped top right. Color of trajectory is the initial position of the object, and the position of the trajectory is where's the robot's hand. So far, so good? Okay, so let's start top right over here. The robot's arm is rotated to the left, and we can see this light colored trajectory, which represents that the robot's arm is left, but the object was dropped top right. What does the robot's arm immediately start doing in that situation? The light colored trajectory emanating from the top left.
It moves in the negative direction.
It moves the arm even further to the left, and then it starts swinging back again. You can trace visually these light-colored trajectories coming down, and you'll notice that around this point, as the object is falling, there are some dark trajectories that are underneath, which represent the robot's arm was rotated left and the object was dropped left. What can you tell me about all the situations in which the robot's arm was to the left, but objects were dropped from different positions above the robot?
Seems like it always had a preference to move the arm one way first and then correct.
Exactly. There seems to be this sort of default position, even if we rotate the arm to the right. It always rotates the arm to the right. Rotates to the left and then starts doing what?
Swinging back and forth.
Swinging its hand back and forth. Again, like BabyBot, if you want to distinguish self from non-self, good idea to keep moving things. If you held your hand still, it may be very difficult to distinguish between self and non-self. So the robot is clearly swinging its arm back and forth the entire time, more or less. What else can you tell me about the behavior of this robot with this controller? When does it know that the object is going to hit front center? We can see that all of these trajectories eventually converge right in front, which tells us that in all these cases, whatever the robot was doing with its arm, eventually its arm was right in front and it caught the object right in front of it when the object got there. When did the robot figure out where the object was going to hit?
It looks like it's like 1.5 time steps after where the bottom is. I don't really know.
It's hard to describe here, right?
Yeah.
Here's a first, is this fifth? 1, 2, 3, 4, 4.5.
So the
Idea?
I was gonna say is top of the arc t equals 0.
Top of the arc is t equals 0. That's right. So this is the moment at which the object was dropped. And then as we move down this cone, this is time as the object is falling towards center front of the robot.
so at time step 3, it looks like everything's been fading to where like the colors line up.
Time step 3, around here.
Or that's when it, like, for example, the dark one is shifting across all the way to the left.
It's shifting across all the way to the left. So you can see by down here, everything seems to have been sorted out. The robot's arm is to the left in all these cases, all these trajectories that are to the left, and all the trajectories to the left are all dark, which means what? What can you tell me about the object during this period?
It means that the arm is to the left and the object are to the left, so very close together.
Exactly. So it's sort of pointing at the object. In this case, the arm is to the left because the trajectories are to the left, and the object is to the left because the trajectories are dark. And then, just at the last moment, it guides the object in with its hand. We didn't ask it to point at the object. All that matters is that it gets its hand there right at the end. Comment?
Should I read into the asymmetry at all? It just seems like there's more like to the left.
It's not quite symmetric, right? It's almost symmetric, but not quite. Not sure what that means.
Could you say it has a pretty good idea, well, I mean, relatively has a pretty good idea about where it needs to go at 1.5 time steps? Because it seems like,
Around here?
yeah, a good majority of paths, almost 4 distinct paths, where it kind of stays in one relative location. It doesn't oscillate across the whole arc.
Yep.
It just kind of stays where it is, and they're all relatively the same color except for the two in the
That's true. It's already started to sort of separate things out, right? So what's interesting here is there are two groupings. There are two initial conditions that we're imposing on the robot. Start with your arm to the left or start with your arm to the right. Sort of those two groupings. But then there is a continuous gradient of positions at which they drop the object top right. But you can sort of see after there's some divergence, there's sort of these four clusters. There's four sort of stereotypical behaviors that the robot tends to perform. Why four? Who knows? Could have been three, could have been five. There could have been no overlap between these trajectories once they started to diverge. The robot could have moved in a different way under every single different condition, but that didn't seem to happen. It's got sort of a repertoire of things that it does. Probably, if you were to go back and redo this experiment and run it again, you'd probably get a different solution. This is probably not the only way to solve this task. When the robot decides that the object is going to hit front center, hard to say, right? Very difficult to tell from this picture. Okay, so kind of interesting. The main point here is obviously motion is a big part of this, and it's not always trivial to figure out what the robot is doing. Okay, now memory. Event number 3. We've got we have a mobile robot at the bottom of the screen. So again, this robot now has 2 rockets, and it can move left and right along the bottom of the screen. We have a single falling object that can fall vertically, it can fall diagonally. And again, the robot has these 7 ray sensors, but you'll notice that they're dashed now in the upper left image, which is reminding us in this case that the robot can see as long as it remains immobile, but the moment the robot starts to move, it's blinded. We turn off the 7 sensors and they just start reporting zeros into the CT-RNN. So the robot is going to have to, quote unquote, figure out where the object is going to hit the bottom of the screen, and then start moving and quote unquote remember where that position is and be there when the object hits. So our fitness function is back to minus d sub I. So we're penalizing for d sub I. D sub I is distance, which is always positive. So again, we don't need these absolute markers here. So we're trying to minimize distance, which is the horizontal distance between the robot and where the object hits the ground. So be there when the object hits. Pretty straightforward. Okay. Similar plot to the one we just saw. We're going to play back the best evolved controller, and we're going to drop a very large number of objects, and those objects are going to hit the ground at different horizontal positions, represented by the horizontal axis here. And on the vertical axis here, we're going to plot what was the horizontal position of the robot in those conditions. How did the evolved robot do in this case?
Pretty much identically to the first one, it seems.
Pretty much like we just saw, right? It's doing pretty well. You see that all the dots lie along the diagonal, meaning that the final horizontal position of the object is more or less the same as the final horizontal position of the robot. But it had a little bit of a harder time here in the center. And it also had a harder time when the object landed far left and far right. Why far left and far right? Why might that be difficult?
Like harder for it to see, like the sensor rays only are so wide.
Exactly. There's a limitation in what the robot can perceive in this case, right? It has this cone of perception going up towards the top of the screen, but objects that at least start top left and top right are going to be hard for the robot to see, which are probably the objects that also more or less hit the bottom of the screen far left and far right. You can see this a little bit more clearly here. Again, same evolved controller, and we're going to drop a dozen objects from different upper positions at the top of the screen, and they're all going to fall straight down, which you can see by the beginning of these vertical lines. And then these lines become diagonal, which is a reminder that what these lines are showing us is the horizontal position between the robot and the object. The objects are falling vertically, so if the robot doesn't move, then the horizontal position between the object and the robot isn't changing, and the lines are vertical. So we can see from this picture when the robot starts moving, and remember that when the robot starts moving, it can no longer see. How does the robot solve this task? How does this particular robot solve this task?
By waiting and then moving once it knows where the object is.
It's waiting, so it doesn't move for a while, and then it only starts moving when it knows where the object is. Maybe, we're not so sure about that latter conclusion.
It must know some kind of velocity of whatever's falling so that it can approximate, like once it reaches the furthest angle, it needs to travel with speed to reach it on time.
Yes, that's true. What else can you tell me about the motion of the robot? Remember, it's blinded, but it can still move however it wants.
It looks like once it goes blind, it just travels at a constant velocity.
It always travels at a constant velocity during any one dropping of an object, but also the same velocity for all of them, right? The slopes of all of these diagonal lines are all the same. The robot always moves at the same constant speed. So we got lucky with this one. This one is more or less something that we can intuit and figure out what's going on. What's the general strategy that it's using here?
It's waiting till the last minute that it has to start moving to get to that position. So it wants to see the longest.
Exactly. One of the unsung building blocks of intelligence is laziness. Do the least you need to do to succeed, right? Let lesser intelligent organisms tire themselves out with complicated and strategies. I'm going to do the simplest thing, which doesn't always happen in evolutionary robotics, but in this case it does. The robot has evolved to always move at the same speed, and if it starts moving at a certain time, it'll always get there. What's the time that it more or less starts moving? How does it know when to move? It obviously starts moving at different times for different object placements.
When the object intercepts its outermost sensors.
So something like that, right? That might be it, when the object hits the outermost sensor. If we drop an object inside, here, inside the cone of perception, it's falling inside the cone of perception, and actually in this picture here, after a while, it touches or breaks one of the outermost beams, and that may be the trigger to start moving. We can see, obviously, when it's dropped, when the object is dropped just at the edge of the robot's cone of perception, it starts moving almost immediate. So I think that's more or less a good description of this robot strategy. When either my leftmost or my rightmost beam is broken, move at this particular evolved velocity constantly, and I'll get there.
Could that also explain why it has a more difficult time in the center? Because that event could never occur, or could occur like so late that the last minute motion is too late.
I think that could also be true. So you'll see these two lines in the center here, the gray lines. Gray represents it didn't do great. It wasn't at the same position as the object when it got there. Maybe those middle dropped objects never quite broke the left and right beam, or they didn't break them in the right way. There's some sort of exception that's going on here, which also exists in the far left and far right conditions, which makes sense, right? For the robot only sees those objects for a split second before they disappear from its cone of perception.
I mean, it would make sense when, if it disappeared sooner in the object, as it falls, it's accelerating. It has less information to work with. It has to, recheck, yes. But in the center, it seems to be aware of it the whole time. So
it's aware of it, right? Quote unquote aware, but it's not triggering this desired behavior, which is move in such a way that you're directly under the object when it gets there. It never moves. Those two center gray lines are perfectly vertical the whole time. The robot sees the object, but it may not see it in the way that it should see it. Scott.
It'd be interesting to disconnect all the center sensors with this weighted robot and see if it does the same job as just the other sensors.
That's it. So there's some additional experiments in evolutionary robotics which we're not going to touch on this course, which are known as lesion studies. So if you really want to understand what either a evolved neural network is doing here or nervous systems, what they're actually doing is to try and knock out or lesion out small parts of the system and see the failure modes. So if we were to lesion out the leftmost and the rightmost sensor of this robot, how much worse would it do? That would give us a hint into how much the leftmost and the rightmost sensor are being relied on for this particular strategy. We might be able to lesion out, for instance, the middle 5 sensors, and the robot does just as well. If you remember back to the gantry robot, that gantry robot did not use all of the sensors that we made available to it. It used a small subset. So we could go inside the neural network and evolved neural network and start to perturb it to really understand what's going on. Okay, let's keep going. Here's a separate set of experiments with the same robot, but now the objects are going to be dropped diagonally rather than straight down. How does the robot do in this case? Same robot, it's blinded once it starts moving, but the objects are now falling diagonally. Again, not bad, has kind of a harder time with things in the middle. You'll notice there's a little bit of curve again and has a harder time with objects that land far to the robot's left or far to its right. Let's take the best evolved robot out of these experiments and again drop objects from different positions at the top of the screen, but they're all falling at the same angle bottom right. What does the robot do in this set of conditions? Is it the same strategy?
Seems to overshoot a little.
It seems to overshoot a little bit. It's not doing great. You'll notice down here at the bottom there's a spread between -20 and +20. Kind of overshoots a little bit. In some cases it undershoots.
Since it can't see while it's moving and the object's moving diagonally, it may be harder for it to know how much to move. Possibly,
right? This may, again, to us it seems like a more difficult task, which may be the case. We can see that there's sort of more or less the same strategy, right? The robot starts moving later and later if the object is going to hit closer and closer to the center bottom of the screen, which is where the robot starts. And when it finally starts moving, it moves in more or less the same way in every case, but obviously does not move at a constant velocity. It jinks left and right as it's moving, but that general strategy is conserved across different drops of the object.
Seems that the motion is still triggered by the object leaving its code.
Perception. Looks like that, right? Looks like the same sort of strategy. Once it can no longer see it anymore, there's no point staying still. You're not going to get any more information. The object's gone. You might as well start moving, which is what it does. Here's a second set of conditions. Same evolved neural network. We're going to drop all the objects from top center of the screen now, but they're all going to fall at different angles. What does the robot do now? Still looks like the same sort of general lazy strategy, right? I'll just hang out until the object leaves, and then I'll start moving. Not always moving exactly the same way, but the same general strategy. Okay, let's move on now to the fourth and the final event. This one is particularly challenging. This is known as selective attention. This is something that we all as humans struggle with as well. Selective attention is the fact that, of course, there are lots of things going on in our field of perception at all times. we are usually attending to or paying attention to one thing at a time. Hopefully it's my voice or the slides or your note page, but of course there are lots of other things going on. Depending on what's going on, you quote unquote decide at certain points of time to switch your attention from one thing to the next. If you do that too much, if you're constantly switching your attention, that's not necessarily a good thing from a Darwinian point of view. On the flip side, if you're always locked on one part of your perception and you're focused on one thing and you completely ignore all the other hints of things that are going on in your periphery, that is also not an ideal strategy from a Darwinian point of view. There's a sweet spot where you need to be able to concentrate on important tasks, but when there's an important signal saying there's something else even more important that you should be attending to, you switch attention. Not an easy thing for us to do, not an easy thing for our minimally cognitive agents to do. This paper, again, was written a while back. Unfortunately, there were no videos of any of these experiments. However, fortunately, a few years ago, someone who took this class tackled this in their final project and did it in PyroSim, so we can see what this actually looks like. What is the task here? What is the robot trying to do?
It's trying to roll in front of the disk, so it's sliding underneath it.
So it's trying to roll in front of the disk, so it wants to capture each of the two objects when they get to the bottom of the screen. What else can you tell me about this task? Why is it difficult? Why is this the final event in our Olympics here? It has to decide which object is going to hit first and switch its attention to that object.
Does it also calculate the velocity of both objects at once? So because like on the right is going out the field of all the sensors, so how would it know where it is?
Does it calculate the relative velocity of the robot? Does it calculate the relative velocity of the pairs of objects? Hard to say. Remember that at every instant in time, the only thing the robot has is 7 numbers, the lengths of the 7 beams. Is it combining those inside the CTRN in some way to compute the relative velocities? When we talked about neural networks a few weeks back, if you have a large enough neural network, it can compute any function between its input and output. It could, in theory, compute the relative velocities of the objects. Is that a necessary computation for this task? Kind of hard to say.
It seems like it's making its final correct motion once the object's like, if there's another object coming in faster from behind, it makes that final decision once it's closer.
Once it's closer, you can kind of see once the object that's actually going to hit is closer to the robot, you can see it, again, switch its attention to that object. It immediately starts to move towards it. Now, of course, these objects are falling pretty fast, so it doesn't always have a lot of time to deal with that situation. What else makes this task difficult?
It's also memorizing, because at the point it gets the first object, it no longer can see the other object.
Exactly, right? So this also incorporates memory. You cannot solve this task without memory. You'll notice at this point where I paused the video, the robot has successfully captured the first object. That first object is occluding all 7 beams, so it's basically blinded by the object that's right in front of it. When I unpause this video, it's once the first object passes, all of the beams are going to be unobstructed, but they no longer touch that second object. But the robot got there just in time. So the robot remembered where that other object was, how fast it was falling, and where it was going to hit the ground and when, right? You can see why this is a little bit more challenging than the other tasks.
The event of catching the object, was that triggered by a touch sensor on the robot, or was that triggered by the occlusion of all the beams at once?
There's no touch sensors. It's just the occlusion of all the beams. That's the only thing the robot sees are those 7 numbers.
Does it, in this case, did it know like when it missed? Like,
The robot doesn't know, but the fitness function knows. And this is a good observation. So in a lot of the experiments we're going to see, when we're computing the fitness function, we are often using information that's not available to the robot. Like in this example here, the fitness function is going to be the sum of the distances between the robot when the first object hits, the distance between the first object and the robot when the first object hits, plus the distance between the second object and the robot when the second object hits. Those two distance values the robot is not given.
I guess with my question is like, if it went for the first object and it missed, but there's still time to get to the second object, but the first object, it didn't include the beams, does it know based on the memory that, oh, I missed that one, but I can still get this one?
Maybe it knows that. Hard to say. Assuming it saw the object that it missed, it may remember that it was there and was not in the right position, but it doesn't ever feel the object. It never touches it. It doesn't know whether it missed or not in terms of actual distance.
Now, this fitness function, that should be, or at least should be the least distance between object and the robot rather than final position or when it hit, right?
When it hit, when the object hits, what's the horizontal distance between the robot and the object?
During training, it would never hit. So.
Well, it passes past the line at which the robot can move along.
Do you mean hit like the end?
Hit the bottom of the screen.
Yeah, not the robot.
Sorry. Yes, hit the bottom of the screen, not hit the robot. Doesn't know that. Okay, so we're summing these two distances, and then when we take the overall average performance of any one CTRNN, we're taking the negative of all those distances, right? So again, we're penalizing for distance. The best thing any one CTRNN can do is get D1 and D2 down to 0 in both cases, right? Okay.
Do you need to have parentheses around that subtraction?
Around the subtraction?
In the fitness function?
Yeah, I think this is meant to be the minus of the entire summation.
Okay.
Sum all of the p sub i's, which are the sums of the two distances, normalize by number of trials and subtract that from 200. So if you get 0 in every distance and every trial, 200 minus 0 is 200. The best fitness value in this case is 200.
200 is the number of trials?
Not necessarily. They don't explain where this 200 is coming from. I think it has to do with the width of the bottom of the screen. If the object always hits bottom left and you're always maximally distant from the object at that point in time, I'm guessing this entire sum would be 200. 200 minus 200 is 0. That's probably the worst possible thing that the robot can do. Any other questions? Okay. So we just talked about this. What makes this task difficult? There are two conditions that make this particularly difficult. The first problem is the passing object problem. As you saw in the video, the objects are placed at the top of the screen, but they're actually placed at different heights. They're not placed at the same height at the top of the screen. Some are initially even further away from the robot than the other object. And the objects also have different velocities. So the object which is initially further away can eventually be the one that's going to hit first. This is what makes selective attention so difficult. You may have got an email a couple days ago about some distant date that you need to sign some form for UVM, and if you don't sign that form, you're not going to graduate. It's distant in time. Probably don't have to worry about it now, but when do you have to start worrying about signing that piece of paper? Tricky, right? Our robot has the same thing to deal with. There are things that are distant in space and time, but they are going to become more pressing before other things which are closer in space and time, but end up being less pressing. You can deal with those things later.
Can't it tell that once one of the balls, surpasses the other ball, it's definitely going to be the first one.
We're going to see, right? Can the robot be lazy here? Maybe it says, I'll just wait. And eventually I'll just wait to see which one is closer and then start doing my thing. We'll see. Maybe it can rely on that. Okay, that's problem number one. Problem number two is you've already identified as the object permanence problem. I've decided that object one is going to hit first, and I'm going to go chase after object one. But object two is falling to the left of me, and I'm going to have to remember that because I can no longer see it. Okay, hold on to that for a moment. Let's have a look at an evolved, this is again the best evolved CTRNN, and we're going to play it back just five times. In each of these 5 trials, we're going to either turn on or turn off one of these 2 problems, which makes this task easier or harder. Let's start upper left here. This is the easiest of the 5 trials. This means that there is no passing objects problem and there is no object permanence problem in this case. Okay. Again, these figures take a little bit to mentally parse, so let's work our way through this. We've got a light-colored polygon here and a dark-colored polygon here. What do they represent?
The paths of the objects as they fall.
Not quite.
Is it the attention that it's giving the object?
Close, again, but not quite.
Is the gray portion the perception?
It's the cone of perception, right? So the black squiggly line, as you can probably figure out, represents the movement of the robot over time. And you'll notice that in this picture here, the black squiggly line is inside the light polygon and also inside the dark polygon, which is behind it. If that line is inside of a polygon, it means the robot can see that particular object. We have the 2 polygons, one for each of the objects. Make sense? These polygons taper and narrow as the objects are falling. Why? What does that mean?
Does that represent the distance of the object, the vertical distance to the robot?
Not quite.
As you sweep an arc, there's just less, there's just not as much area.
Exactly, right? The area, the width at which you can see the object narrows because the object is closer to you. And down here, you've got to be very close to the object to be able to see it. There's not a lot of wiggle room, literally, to see the object. But when the objects are up here, the robot can move just a little bit and sweep its very wide field of perception across the underside of the object. So as the objects get closer, it's harder for the robot to see them in the sense that there's a narrower width in which the robot can move and still see that object, right? So you better decide quickly because it gets harder the closer the objects get to the bottom of the screen. Okay, let's stick with this picture. What do the 2 straight lines represent? The squiggly line is the motion of the robot. The 2 straight lines are
The trajectories of the object.
the trajectories of the objects, right? So it's only the robot that's oscillating back and forth. The objects are falling at a constant, falling in a constant direction towards the bottom of the screen. One polygon is lower than the other. What does that represent?
Catches one object and then it moves, I guess, the cone perception over to catch the second object.
Exactly. So it's catching the dark object corresponding to the dark polygon later. The vertical axis here is time. So as we move down any one of these figures, we're moving later in time. So the light object hits first, and then later in time, the dark object hits the bottom of the screen second. Okay. How do we know that the robot caught the objects, caught both of the objects in this case.
They were centered in its field of vision.
Centered in its field of vision, right? The squiggly line meets up with the straight line right when the polygon ends, which represents when the object hit the bottom of the screen. So the robot was there to catch the light-colored object. What did the robot do immediately after co-locating itself with the light object?
Lined up with the second object.
It immediately headed over to the right and stayed underneath that second object and caught it in plenty of time. No sweat, right? This one was super easy. Let's go back to this point in time right here. What could the robot see when it caught the first object? Could it see only one of the objects? Both? How do we know?
You can see them both.
Can see them both, right? So the squiggly line is inside both polygons at that time. So the robot is catching one. Now it may not be able to see it because the closer object is occluding all 7 beams, but the moment that object drops past the robot, it immediately sees the second object and clearly knows what to do in that case. Make sense? Okay, this is an easy case. Let's make things a little bit more difficult. By now, we're going to introduce the passing objects problem. We're going to drop both objects, but the object that is initially further away is going to move faster and hit the ground, hit the bottom of the screen before the initially closer but slower moving object. What do you think the horizontal dashed line represents?
Where the objects pass each other.
Where the objects pass one another. What is the robot doing before the objects pass one another?
Moving back and forth.
Moving back and forth underneath both, right? The robot says, I don't know, or we think it doesn't know. It's acting as if it doesn't know which object is going to hit first, and it's acting as if it's trying to decide, quote unquote, which object to go chasing after first. When does the robot decide which one to go after? Does it know which one to go after?
When it can only see one.
When it only sees one?
Are you talking about the bottom left? Sorry.
Talking about this panel here.
When it passes the object.
It looks like pretty much right after the faster moving object passes the slower moving object, it gradually moves underneath the light object, which is the one that's going to hit first, right? It seems to have made the decision and is ready to go. All right, it catches this one, and then like before, it immediately starts chasing after the second one, because at the moment at which it catches the first object, it can immediately see the second object, and off it goes, right? So this robot can solve the passing objects problem, at least in this case. Let's take the same evolved neural network and expose it to the inverse situation. We don't have the passing objects problem here. The closer object is the faster moving object, and it's going to hit first. But we now have the object permanence problem. There's a period during which the robot cannot see both objects. What is that period?
When the cones separate.
When the cones separate, you'll notice the squiggly line stays within the light-colored cone, or the light-colored polygon here, which makes sense. That's the one that's going to hit first. It's tracking it, and at the moment it catches the light object, it cannot see the dark object. What does the robot do in this case? Does it start moving back and forth under the bottom of the screen looking for the second object again?
Just goes as fast as it can in the direction that
It-
the other object has.
It immediately starts heading, we don't know if this is as fast as it can go, but pretty fast towards the other object. It knows, it remembers, it at least remembers on which side the object is, because it immediately starts heading in that direction. There's none of this active scanning back and forth to re-find the object. Off it goes and gets there in plenty of time, and then leisurely sweeps underneath the object, tracking it as it falls and captures it. Great. Okay, let's really challenge this robot now. We're going to introduce both problems at once. The objects are going to pass one another, and the robot is not going to be able to see both at the same time after a period of time. Tell me about how the robot solves this one.
Looks like it commits once it sees one object past the other, because it oscillates at first, and then as soon as the object passes, it commits.
Exactly. So it looks more or less like this, right? It's sweeping back and forth underneath both, and the moment one passes the other, then it starts to bias its motion towards the one that's going to hit first. And once it successfully captures it, does it have to go looking for the other one, or does it know where it is?
Looks like it knows where it is.
It knows where it is, right? It starts hightailing it in the other direction and gets there just in time to capture it. All right, that's enough of this robot showing off. Let's make things really hard on it, and let's see how it does. Same thing, passing objects and object permanence problem, but it's more difficult. More difficult how?
Both objects moving in the same direction.
Not quite, they are moving in the same direction, but that's not what makes this more difficult.
It can't see the second one when it starts.
It can't see the second one exactly. It starts right here, and just at the beginning, it can see both, and now it no longer can. So let's be a little bit more specific. What is making this so difficult?
It has to it sees it for half a second and has to kind of perceive its motion based on that short period.
That very short period of time. It can't be lazy and wait for the faster object to get closer. It needs to make its decision about which object to chase after before the faster object has passed the slower object. Right? So it's judging two different events and trying to judge the relative urgency of these events, and makes the decision about which event is more urgent before it's literally closer to it in space and time. This is, again, challenging for this robot, challenging for humans. It's a hard thing to do, but it seems that our robot is able to do that. It correctly decides, or it correctly perceives that the light object is going to hit first, tracks after it, and once it captures it, even though it only saw the dark object for a split second, it remembered where it was heading, or it computed where that object was heading, and headed in the right direction, and got there just in time to capture it.
In this diagram, does the broken line signify when one passes the other, or does that signify when object permanence occurs?
The dotted line represents the first. It represents when the objects pass one another. The object permanence problem comes into being the moment that the two cones separate from one another, right? Once the line, once the movement of the robot is perceiving one object, but that line is no longer inside the other polygon, that's the object permanence problem. It cannot see the other object.
So in that diagram, it's kind of like, I can't really tell it's with the contrast on the projector, but does the moment when one passes the other occur during?
Yes, it's very hard to see. Let's zoom in. So you'll notice that the objects separate from one another just before the objects pass one another, which forces the robot to decide which object is going to hit first. You can't wait until they both pass one another to decide.
No longer rely on that event.
It can no longer rely on the event of waiting for the faster one to be closer to it. It's decided, it's made the decision before, while the faster one, which is the lighter object, is still further away from it.
Was the robot able to solve this case
training on all the other cases, or did it have to learn this case specifically?
That's a good question. It's not mentioned in the paper. Did this situation actually arise during evolution? Or were the other conditions enough to challenge the robot so that when it saw this more challenging situation, it was still able to solve it? They didn't say.
I feel like if it didn't see the objects past one another, it's in the other diagrams, it seemed like it wasn't going for either of the objects. It was just kind of like waiting to see the pass.
Right.
And so my instinct would be that it would not even go for one of them if it just saw one. It would just stand still and wait for one object to pass the other.
Possibly.
But, so this is surprising to me.
Yeah, yeah. So maybe it saw this condition during evolution. It saw the case where it was forced to decide before the objects pass one another. That could be the case. Okay, again, an interesting problem to tackle for a final project if you're interested. Okay, that concludes our minimal cognition Olympics, and we'll move on to lecture 10. This is not really an early experiment in the field, but I've added it at this point in the course because it sort of follows on from the minimal cognition experiments. Obviously, we're not just interested in Space Invader robots and 2 rockets and so on. We want to be able to evolve robots that are able to exhibit the building blocks of intelligence, but we also then want to be able to gradually complexify the robots and their task environments, transfer them from simulation to reality. We want to start here, but move up to robots that are complex enough to get around in the world with us. So this robot that we're going to see in lecture 10 is more complicated, and it's building on some of these other building blocks we've seen so far. Okay. Let's introduce this 5th building block now. This is known as active categorical perception. This is, again, something that's relatively challenging for humans. As you're sitting there quietly, you are passively categorizing objects in your environment. You can distinguish the screen from me without having to physically interact with us. You can passively do it visually from a distance. How did you learn to do that? How did you learn to recognize objects at a distance? This is still a bit of a mystery in developmental psychology as humans develop from infants to adults. Most children don't sit passively and observe their environment. They will reach out and grab anything that they can and actively manipulate them. Most children at young ages will grab objects and put them in their mouths and bite on them. Why?
More nerves.
There's a lot of nerve endings in your mouth. If you want to learn about objects, one of the best things you can do is put them in your mouth, bite on them. Is this food? Is this something that's hard, soft? Is someone going to get mad at me if I bite on this object? So a lot you can learn about an object by physically manipulating it. That's what the active categorical perception means. Okay, so children do this instinctually, which is a hint that it's probably a good thing to do. You can imagine taking a child, strapping that child down, and not allowing them for the first few years of its life to touch anything, to train it to look at the world and reward and punish that child depending on how well it does at perceiving objects in the world. As you can probably imagine, that experiment has not been done. That is exactly what we do with our machines. We feed our machines millions of images or videos from YouTube. They are not allowed to touch, or they're not able to touch or physically interact with any of the objects that they see in those images or videos. And it turns out with enough images and videos and enough computational power, our machines can eventually figure this out. But is this really the best way to train machines to understand objects in their world? It's definitely not what we do with our children. There's a big disconnect between the way we train our children and the way we train our machines. So let's look at a way of enabling machines to actively interact with their world and learn about their world by physically and literally pushing against the world and observing how the world pushes back. When you do that, there is something magical that happens. And this is a simple cartoon example to show you, to illustrate the potential of physical interaction. Imagine that I place these 11 physical objects in front of you on a table. Before I do that, I blindfold you. and I tell you that I'm going to place 11 objects in front of you, one after the other. You're blindfolded, and I give you an instruction, which is to distinguish the round objects from the edged objects. How might you interact with these objects to discover this distinction?
Try and feel how pointy they are.
You might feel how pointy they are, so you could grab the object, and you might then give me a score from 1 to 10 about how pointy they are. Imagine instead you simply placed your palm on top of the object and moved your arm left and right. What would happen if you did that particular action with each of these 11 objects?
Some would roll well and some would roll less well.
Some would roll well and some would roll less well. Can we be a little bit more specific than that?
The amount that they roll would correlate directly to how edged they were.
Possibly. Are they all going to roll more or less?
I'm thinking that if it's like a sphere, the height of your hand would remain the same, but if it was like a square, it would move up and down.
Absolutely. So you can sort of feel the proprioceptive senses in your arm changing as you change the objects, as you change your interaction with these different objects.
I feel like some of them will roll and some of them just will not roll.
Some of them will roll and some of them just won't roll. So a lot of the ways in which you could interact with this object, like grasping it, will give you sensor information that changes continuously. You're going to give me a score between 1 and 10 about how edged it is or how much your arm is bouncing up and down. But other ways of interacting with the objects will tell you that there is not 11 objects here, but there are 2 classes of objects. Those that are rollable and those that are slidable, for example. Where that class boundary falls depends, of course, on how hard you press the object, how deformable the object is, the friction properties of the tabletop, and so on. But the magic is that, as you can see here visually, there is no distinction, right? There is a smooth transition from round to edged. But if you imagine interacting with these, suddenly there springs into life a barrier. Everything on this side acts in one way, and everything on the other acts in another way. If you think about your raw perception, you have photons that are falling on your retina, you have pressure waves that are falling on your inner ear. That's all analog signals. Everything is a wash of continuous values, but that's not what it feels like, right? You can distinguish slide from non-slide. The world to you is discrete. The things that you sort of pull out from the continuous wash of perception that's always flowing over you, discrete things, friend, foe, food, poison, opportunity, danger. Imagine you weren't able to do that. The world was just always a continuum for you. It seems like it would be very difficult to know what to do in such a world because you'd have to do something different for every particular instance. If, however, you're able to take your analog world and discretize it into these important bins, you can come up with distinct strategies for dealing with friends and dealing with foes. Where do those categories come from? Interaction with the world.
I feel like something like that is more gray than simply like friend or foe, you know, there's different levels of
Absolutely.
interactions you have with different people.
Of course, right? So at a first approximation, there's friend and foe, but of course, the devil is in the details. It's not as simple as that. I'm oversimplifying here, for sure.
So like, in terms of this like big information, you know, bombardment that we get from our senses and like what we focus on or not, like I can choose to look at you because you're talking, and I feel like that's kind of like, I'm very active in listening to you and understanding what you're saying, but then there's other senses like smell where, you know, oh, I'm smelling this fresh baked bagel or something, but I've been in the room a while now, you know, someone who just walks in will go, oh wow, bagels are in here, but I'll be like, I can't even smell the bagels.
That's true. So novelty of stimulus is important, and it impinges on your ability to selectively attend to events like the bagel or my voice, which is related to the previous agent that we just saw, selectively attending to different things. But when we say attending to different things, where does the concept of thing come from in the first place? It seems obvious to us. The world is made up of humans and tables and chairs and notebooks and so on. It's obvious. But remember that thinking about thinking is misleading. The world is not really made up of tables and peoples and chairs and so on. It's made up of photons and pressure waves in a continuous manner, and your brain pulls out of that those continuous signals discrete categories. And how humans do that and how we might get robots to do that is an open challenge. That's the point here of the ACP robot that we're going to see in a moment. Once you can see discrete classes, then you can selectively attend to the bagel or the instructor. But you need to know that those categories exist in the first place. Again, we currently train our machines by giving them these categories. Usually, find the cat in the YouTube video, right? We give it the concept cat already. Humans don't seem preloaded with that ability. We somehow have to build those categories ourselves from the raw continuous perception that we're receiving all the time that we're awake. Okay, so again, coming from an embodied cognition point of view, the key to make these categories seems to come from physical interaction with the world. When you push against the world and the world pushes back, it's still all continuous signals, but the results of those actions seem to start to separate out into discrete classes. The object rolled underneath my hand, and then suddenly the new object doesn't. It now slides across the table as I move my hand. Okay, that's the idea behind active categorical perception. Assuming that you, as an organism or as a robot, stumble across an action that creates these categories, and those categories are somehow useful to you, it's still, as was pointed out, not always obvious whether someone or something is friend or foe. Those boundaries between those categories are always somewhat blurry. A lot of what animals and humans seem to spend their cognitive effort on is sharpening those boundaries. Is this person actually my friend or my foe? What can I do to sort of figure that out? That's another important part of active categorical perception, which is to act on the world to sharpen those boundaries. And the way we do that is to try and reduce within category differences. I have a bunch of people that I know, and all of these ones who I'm pretty sure are my friends, when I interact with them, there's a common thing that happens. That's the thing that forms friend. That's when I ask a certain question, get a certain response, I have a certain conversation. Those conversations all have a common form, and that tells me that this is a friend and not a foe. And I can choose what those questions are. I can act in a way that reduces differences between each of my friends. I can interact with them in a way that they fall into the same sort of category. How do I act in the way to do that? I'm rolling my hand along the top of these objects, and I'm going to alter my pressure to sort of figure out exactly where this boundary is. I can also act in a way that magnifies differences. This person, I'm not sure if they're friend or foe. I'm going to ask them a series of questions that'll sort of magnify that difference. Or are there these two people and I'm not sure how close together they are in terms of friend or foe? I'm going to try and sort of push them apart, find the boundary. Can I act in a way that magnifies the differences between objects that exist in different classes? In all the people that I know, when I talk in this way, that's friend. And when I talk with them in this way and they respond in that way, that's foe. I'm magnifying these differences. So we're going to try and act in a way that gives rise to these categories. And then additionally, the robot is going to act to try and sort of figure out, try and reduce the differences between rollable objects and reduce differences between slidable objects and magnify the differences between my interactions with these two groups. Okay, let's see a robot that's able to do this. This is clearly not a minimal robot anymore. This is a anthropomorphic robot. It is more or less humanoid, at least in terms of its single arm. It's missing the rest of the body, but this will do for our purposes. We've got an arm here that has, we have an arm here that has 7 joints, J1 through J3. These are all rotational hinge joints that you should all be familiar with by now. So at the shoulder, there are 2 hinge joints, J1 and J2, which allow this kind of motion. If I change J1 and J2, I can rotate my arm relative to my torso in this way. What does J3 do?
Is that a linear actuator?
It's not a linear actuator. That would mean the robot could lengthen its arm, which we can't do, and this robot also can't do. It's twist about the long axis. So we can kind of do this with our bicep. It allows the arm to rotate about its long axis relative to the torso. So J1, J2, and J3 together allow this kind of motion. J4 is straightforward, that's the elbow. J5 allows the hand to twist along the long axis relative to the elbow. That's 5. And J6 and J7 are left, right, and up and down. Okay, pretty humanoid, not bad. Let's have a look at the hand. The hand has, the hand has all of the cyan cylinders that you see in the hand are rotational joints. So there's a lot of them. Obviously, there's a lot of things we can do with our hand. But in the neural network we're going to see in a moment, there is one motor neuron that controls all the motors, controls all the joints in the hand. And that one motor neuron, when it outputs a positive value, the hand does this. And when that single motor neuron sends a negative number to all the joints in the hand does this. So we have multiple joints, but they're not independent. They all move together. That's something we haven't seen before. That is something that you can do in PyroSim. You can create multiple rotational joints and assign the same motor neuron to those joints, so they all move in concert with one another. Okay, what are we going to do with our robot? We are going to perform a total of 16 trials with each CTRNN that's controlling the robot. We're going to do 2 sets of 8 trials, which will give us the 16. In the first 8, we're going to set the initial position of the robot to A, and in the second 8 conditions, we're going to set the initial position of the arm to B. In each of the 2 positions, we're going to put 8 objects underneath the robot's hand. It's not actually 8 objects, they're just 2 objects, but each of those objects are going to be placed at different angles or at different orientations underneath the robot's hand. So from the robot's point of view, there are 16 objects. The CTRNN was played out 16 times, and it's probably going to get 16 sets of sensor data. And we wanted to reduce those 16 sets of sensor data into just 2. We want the robot to tell us, were you in the presence of the sphere or the ellipsoid? So again, from our point of view, looking at the robot and the objects from our point of view, this looks trivial. You can visually see there are 2 objects. The robot does not have a camera. It can't see these objects. All it can do is feel them. So this robot, like the thought experiment we just walked through, this robot is blindfolded. It can only feel the interaction of its hand and the object. All right, let's have a look at the neural network. This is a CTRNN. It's organized more or less like we've seen before. Here's the input layer, here's the hidden layer, and here's the output layer. Let's start with the input layer. There are 7 arm proprioceptive sensors. What values are arriving at those 7 proprioceptive sensors?
The rotation of the joints.
Exactly, the angle of each of the 7 rotational joints in the arm. That's pretty straightforward. So at every point in time, the robot can feel the angles of its arm. And there are 10 tactile sensors, 10 touch sensors in the hand, 2 in the 1 in the thumb, 1 in the palm, and then 2 each in the remaining 8 fingers. So a total of 10 touch sensors in the palm. And a final 5 proprioceptive sensors in the fingers, which correspond to the angle of the fingers. I just finished telling you that the hand always contracts and opens at the same angle for each of the 5 fingers. But that's not what happens in reality. The angles are actually different. Why?
What if there's an obstacle against one of them and not the others?
Absolutely. So as the robot starts to manipulate the sphere or the ellipsoid, then the angles in the fingers are going to diverge from one another, and those 5 angles of the 5 fingers are reported into the input layer of the CTRNN. I think we will leave things there for today. You have a quiz due tonight, and I will see you on Tuesday. Have a good day.